Now you can see the first graph 2 2 2 have 2 to 2 connections. Is V1 have 2 connections here and here. Second graph here and here. V3 here and here. 1 to 1. V1 have 1 connection here. V2 have 2 connections here and here. And V3 have 2 1 1. Here 2 connections. V2 have only 1 connection and V3 have 2 only 1 connection. Fourth graph have V1 1 connection, V2 1 connection, and V3 0 connection. Yes, of course. Fifth graph, V1 have only 1 connection, V2 have 0 connection, V3 have also only 1 connection. 6. 0 1 1. V1 have 0 connection, V2 have 1 connection, V3 have 1 connection, and seventh graph and eighth graph have some of them. The V1 have 1 connection with V3, V2 have 1 connection both with V3, and V3 have both of them connections here and here. And eighth connections is about have 0 connections with nobody with no, and it have 0 0 0. Yes. So we done the first exercise.
Wait. What the hell?
How many edges are there in each group? Let's see. First, I need to write that. How many edges? Oh, I write it. So let's see carefully. In the first graph, we see the 3 edges. V1, V2, V3. 1, 2, 3. In the second graph, we see the 2 edges. Here is, and the third, we see the only 2 edges, and 4 only 1. In the fifth, only 1. In the sixth, only 1. You see it? And with seventh graph, we see 2 graphs, like in second and third. And in 8, we see no edges, because there are no degree sequence. Okay, that's solved. Oh, I forgot. That's solved. What is the degree? Now I wrote that upper than the each graph. Here's a 2 2 2. Here 1 to 1. Here 2 1 1. Here 1 1 0. In the 5 1 0 1. In the 6 0 1 1. In the 7 1 1 2. And 8 0 0 0. Both of the numbers I speak before my speech. Write it. Here we done. Thus my asking is no. Is no, because in the pseudographs we have about loops, we have about some of multiply edges or repeated loops. So if we use that, we can see the infinitive quantity of the graphs, and in our questions we need to show the edges. If we use the pseudograph, we can see the infinitive quantity of edges, so that is impossible, and so we can't use some of the pseudographs. So that was the exercise 2. We done with it. Аплодисменты.
Ничего себе.
Exercise 3. Oh, I need to write it. And now you think, that's impossible. That's impossible. Every vertex is adjacent to 2 vertices, and every edge is adjacent to two edges. But now we can explain to the K3. K3 is the graph who have three vertices, and every vertices have adjacent to two vertices and have two edges. Yes? Let's explain how I said it was K3. Let's draw that graph to understandable. So here's a V1, here is a V2, here is a V3, such that every vertex is adjacent to two vertices. Let's try V1 with V2. Now you see the V1 have adjacent to the V2 and V3, two vertices, okay? And every edge is adjacent to two edges. Now we see the V2 and V3, no edge. Let's troubleshoot that. We see the triangle, or in how said Pro is K3, not Kia. But I want Kia K3. K3. They have the two edges, V1, V3, V2, V3. Or let's try. Is adjacent to two edges. Every edge is adjacent to two. One edge and adjacent by two. Here and here. Yes, yes. Every vertex have two vertices. V2 have V3 and V1. V1 have V2 and V3. And V3 have V1 and V2. Let's look more like. So that exercise is done.
Невероятно.
Exercise 35. Can there exist a graph with 13 vertices? Let's write. Exists a graph
She didn't have to cut me off. We were nothing. Your love should treat me like so love.
13 vertices. 13 vertices, edges 31, and we have 3 vertices with degree 1 of degree 1 and 7 vertices of degree 4. Let's make some уравнения. We have 3 vertices with degree 1 plus 7 vertices with degree 4, and it's equal to 31. By the formula of edges, the sum of all vertex degrees must equal twice the number of edges. Okay, sum of degree. So 2 multiply 31 plus A plus B plus C is equal to 62, and A plus B plus C is equal to 31, because 31 is goes back and with znak minus, and so the sum of 31. Can we explain that? Yes, we can explain. The last of vertices is equals to 11, 10, and 10. So we have the vertices with, let's make a sum of graph. Let's try.
shall die.
Now we have some downgrades with video because my storage is full. Exercise 35, section 2. Can there exist a graph with 31 vertices? Three vertices with degree 1, and 7 vertices with degree 4. And let's try 2 example. And we have I just add 3 vertices. Sorry, I not 31 vertices, 13 vertices and 31 edges, and 3 vertices with space. I said about space degree. Okay, let's try. So how we know with sum of the formula of degree, sum of degree equal to 2 multiply e, where e is edges. So 2 multiply 31, our edges is 62. And if we use 62 minus 3 vertices with 1 degree minus 7 vertices with 4 degrees, we see the 31. Oh, and what we can do with it? Sorry, I forgot. Hey, what we can do with that vertices? With that vertices, we can use the 3 vertices with space, and just improvise that numbers. It must be 12, 9, and 10, because 12 plus 9 plus 10 is 31, or 10, 11, it also 31. So yes, we can explain that graph if that connected. For example, if the 12 for that is connected with each of graph excludes the first line connected first line and with one connection, and two connection with who connect with them to ask the compliance with that connection. Okay, with that. Okay, you understand? For example, is V13 is connected with V1. If he have one connection, V2 have one connection, and some V3 space V3, and that connected, and that not connected because I said the 12 is connected with each without one of them, and that one of them is may connected with other groups, not with Z3, because in compliance we see we see the we must connected, and other of them we can use the 4 degree, because in my choice we can see the 4 connection is most available. So yes, we can explain that graph, but I cannot draw that because that will be very longer, and many attempts that will be my first attempt and second attempt. You can explain that. So thank you. My name is Kakemov. See you next time.
Pablo.